Hi all, welcome to Penn's Power Corner. I'm your host Alia Shokat, Editor-in-Chief of Power Electronics News. Today we'll be speaking with Johannes Schoiswohl, head of the GaN Business Line at Infineon. It's good to meet you, Johannes. How are you doing today?
Very good. How are you? Nice to see you.
It's nice to see you too. Um, so we can talk about maybe the recent release in late February. Infineon released four new CoolGaN Drive half-bridge 600-volt G5 devices. And this expands the CoolGaN Drive product family that was first established in 2024. Can you describe the additions in more detail, and how do they differ from the other CoolGaN 600-volt half-bridge G5 products?
Yeah, very good question. Thanks for asking. As
Um,
you said, we just released the full portfolio of this CoolGaN Drive half-bridge portfolio. Late 24, we did an early announcement, and now finally, so to say, we have the full productization, the full portfolio is rolled out. So essentially what we're doing, we're adding additional product portfolio to this initial early portfolio that we had. What I want to highlight is that this CoolGaN Drive, which is typically a gate driver and two high voltage GaN switches, they really help designers and help customers to use GaN in the sense that it's easier to use, right? Often we see a challenge in the gate driving around gallium nitride per se. And this is now really a product that helps to overcome this barrier and really accelerate the market adoption of gallium nitride.
Okay. I understand the CoolGaN G5, these devices, the drive devices, they achieve a low propagation delay of 98 nanoseconds with a minimal mismatch. How is this relevant for motor drive designers, and what design aspects does this realistically unlock that may not have been practical before?
So the precision timing is very critical. When we can reduce the so-called dead time in these applications, what it allows to do is to increase switching frequencies. And with the higher switching frequencies, we can then achieve system advantages like miniaturization, right? You can reduce passive components on the one hand side. On the other hand side, what you can also do is you can increase the precision of the motor drive. So especially when it comes to servo motors and to very fast spinning motors, this is of course an advantage. So therefore, having very short propagation delays and minimal mismatch between the channels in the gate driver really helps to get to the system benefits of making things smaller, making them more precise, and eventually also more efficient, right? So this is really, I would say, the three key elements that are enabled by this high precision, low latency propagation delay that we have in these gate drivers.
Gotcha. And maybe we could shift to the G5 devices. This generation is reported to have a figure of merit that's 30 to 40% better than the industry. What's specifically changed in the device architecture to get there?
Yeah, so in the device, what we do, let's first talk about the figure of merits. So a figure of
Yeah.
merits means that there are so-called performance relevant figure of merit. So what we reduce is per RDSON or per die area, the relevant gate charge, output charge, output capacitance, and so on. And in this way, for a given RDSON, you have much lower parasitic losses. And that is really what this Gen 5 technology delivers. It delivers higher performance even versus the previous generations, and we are very convinced also versus what is out there in the industry. What we really did is that we further advanced, so to say, the device concept and the device physics that we are utilizing. I will not go into every detail here because there's of course also certain IP there. But by further progressing, so to say, the so-called GIT concept as we have it, the Gate Injection Transistor for the high voltage GaN, that allowed us to further reduce these parasitic capacitances. This
Okay.
is on a very
Okay.
high level how I would say that. Yes.
Okay. I appreciate it. Thank you. I'll get back to the gate injection transistor. But I wanted to talk about BDS a little bit. Bidirectional switches. CoolGaN found a pretty high profile win in Enphase's IQ9 microinverters. Can you explain what specifically makes BDS a better fit than back-to-back unidirectional switches for applications like this?
Yeah, so I think one of the really key advantages of gallium nitride is now that it's a lateral device and that you can monolithically integrate certain aspects. Let's put it like that. So normally, what you just said, right? When you have unidirectional switches, you take two switches back to back, and then you can also implement this functionality. But now with GaN, instead of having two dies that have a certain die size, we can really monolithically integrate this into an overall chip and an overall die that is smaller than the two unidirectional switches.
Okay.
And that, of course, is a huge benefit in terms of size, but definitely also in terms of cost. Yeah, because we can indeed up to 4 switches when you have back conduction in both directions and back to back, we can up to 4 switches can be integrated into one die. So that is now really, yeah, the perfect semiconductor switch. It's blocking in both directions. You can, with 2 gates, turn on very precisely each channel. And so in this way, you can now have a functionality that you never were able to do with a standard unidirectional switch. Of course, it also means that you need to have topologies where that makes sense. Yeah, so wherever there's a back-to-back arrangement, there such a switch makes a lot of sense. And such a back-to-back arrangement you find, for example, in a so-called cycloconverter. Yeah, and the cycloconverter is now used by some customers, and there this bidirectional switch delivers all these benefits that I just mentioned, right? Together with GaN again, so you can go to higher frequencies. Anyway, it's already a smaller device. It's more efficient. You can reduce the passive components, and so overall the size of inverters, for example, can shrink. So that is the beauty of this bidirectional switch.
Okay. Can you walk me through the quasi common drain design with a double gate structure, as well as you were saying, Infineon's gate injection transistor technology? I understand that it's used in the high voltage GaN BDS technology.
Yeah. Yeah, so I said in the end, I think it's a little bit what I already said, right? So we
Yeah.
merged our 2 switches together. And then you, of course, need to decide, do you merge common source or common drain? So the decision was to do this common drain. And then you have 2 separate gates where you can then control each channel. And in this way, yeah, you get this bidirectional GaN switch.
Gotcha. Okay. Can we talk about how the gate injection transistor technology addresses dynamic RDS-on drift and the gate fragility of GaN?
Yeah, so dynamic RDS-on is an effect that is long known in the industry when it comes to gallium nitride. And when we worked on this technology, we early on understood that this is something that must be addressed because it's horrible, right? When you go into an application, you run your device, and over time it just gets higher. RDS-on means it getting hotter. That means correspondingly, you need to over-design to a certain extent. You need to use lower RDS-on devices that you would normally need if there would be no dynamic RDS-on. So addressing this has impact. It has impact on how big the device is. It has commercial impact and reliability impact. So therefore, solving this is very important. Now with this GIT technology, what we have here is a very special gate structure where there's a continuous current flow through the gate. It's a very small current flow actually, that when the device is on, that actually injects continuously holes into the surface potential, and this way stabilizes the dynamic RDS-on. It's a very intricate physical process, so there's many lateral layers in a GaN device. The electrons move along, so to say, also these layers. And wherever there is an interface, there can be charge trapping. And that eventually leads to such dynamic RDS-on effects. And this we counterbalance by this GIT technology. So it's a very special approach in order to make sure that this dynamic RDS-on is under control. And you will see if you look at our data sheets and if you test our devices also, you will see that the dynamic RDS-on is not existent anymore. So with this special technology, we really have it fully under control to the benefit that it's a very reliable product and that you don't need any funny workarounds that also commercially are not viable, and you can use the device as is.
Thank you. And I imagine, as you were saying, the sort of intricate physical process of there's a GIT specific drive nuance integrated within the ICE drivers, the external gate driver ICs, as well as the GaN devices. Could you describe more about that nuance?
Again, sorry, can you repeat the question?
Oh, sorry. Could you maybe describe more about the GIT specific drive nuance integrated within the ICE driver, gate driver ICs?
Yeah, so we have, when we use our gate drivers, we need to make sure that we ensure that this continuous small current is actually injected into the gate, right? So therefore, the gate driver design needs to adjust for that, because what you typically do is you have a so-called voltage controlled gate versus this would be more of a current controlled gate. So this difference is reflected then in the gate driver architecture and then of course integrated into the iGaN product.
Okay, okay, thank you. All right, that's very helpful. Maybe we can shift to the 300 millimeter program.
Okay.
Um, so the first customer samples were announced in late last year. What can you tell us about how the rollout is progressing?
Yeah, so the first customer samples, as you said, late last year, Q4 25, we were able to sample a range of customers. It's actually progressing, I would say, very well. We see a lot of interest in moving also to the 300 millimeter. We actually want to do it in a way that it's a seamless transition for customers. So what we had on 8-inch, we will also offer on 300 millimeters. So it's a one-to-one transition. The product specification is the same and so on. So for customers, it's very easy to transition. But the benefit, of course, is that we have now a completely different scale when we move to 300 millimeter, right? So within Infineon, we have already 300 millimeter power. We do this for silicon since many, many years. And so we can reuse a lot of the tools that are there. So as the market in GaN might accelerate quite quickly, we can tap into these capacities, right? And if there's a certain rollover, so from silicon to gallium nitride, we can use these capacities and scale up very quickly with the 300 millimeter. And I think that is a key benefit when it comes to 300 millimeter. It's supply security and supply insurance for a market that is still early, and there's always a certain uncertainty, but it could move quite quickly up. And so here we have capacity practically today installed in order to fulfill the market demand.
Okay. You basically answered my next question which was basically what the transition from 200 to 300 millimeter actually meant for customers designing with CoolGaN today. Was there any additional factors as well for customers?
I think I said it, right? So it's an easy
Yeah, yeah.
transition. So I have not much to add from my side.
Okay, okay. And what are the major obstacles to 300 millimeter GaN production, and how can they be overcome?
I would say the key challenge that we saw was really one of the very first process steps when you do gallium nitride power semiconductors, and that is when you have your wafer and you grow your so-called epi on top of it to do this in a way that you can do it on 300 millimeter. So the lattice mismatch between silicon and GaN is huge. That means there's a lot of strain and stress, and to keep this stable and to have a manufacturing process to run 300 millimeter GaN, that is really the key challenge. So it is about manufacturability. That is the key topic. And that I believe we have now solved. I said we are already sampling. We are moving towards productization, and towards the end of next year, we then really want to fully ramp on the 300 millimeter.
Thank you. Maybe we could move towards more general GaN questions. How does owning a fab change your ability to compete against fabless GaN players reliant on foundries?
So I think what it allows us to do is especially two topics. There is the topic of speed and there's the topic of innovation, right? So when we talk to customers, you can imagine there are sometimes very special requirements that customers might have. And to implement that in gallium nitride might mean that you want to change your front-end process. Yeah? And when we want to change the front-end process, you need to own your own fab and your own technology. So, and that goes even back to even engineering the epi to certain requirements. So what we do at Infineon is we always want to understand very, very deeply, for example, the mission profile, the application profile. We do not only do JTAG qualification, of course it has to be done, but beyond that, we also want to understand how is the device used, and we really deeply go into that and then engineer from these customer requirements the process to really make sure that the device fits this application over lifetime. And so customer requirement has a direct impact on process. And this connection, of course, if it's all under one roof, we can shortcut, so to say, this connection and very quickly transfer these customer requirements into process technology that then we make the products out, where we then do the testing, where we do the packaging, where we do the backend testing, and that then we deliver to the customer. So it's really an end-to-end supply chain ownership that also gives you, of course, a lot of security of supply. Yeah, so we're not depending then on maybe a test house left and a packaging house right. So that is a key strength, I would say, now on the gallium nitride products that we're having.
Thank you. I was just going to close out with one more question. In your view, what do you feel is the most underappreciated GaN story that the industry might not be really talking about today?
I think there's a lot of talk about GaN in the industry, but I think what we will see much more coming is medium voltage GaN, 100 volt, for example, 80 volt GaN. The benefit of these voltage classes in gallium nitride versus silicon is just tremendous. And I think only now customers start to discover that. But once they see it and they really implement it then in their system, they are really eyes wide open, right? And I think over the next 12 months, you will see exciting product releases from Infineon. You will see a big adoption, I believe, of these technologies, especially also in AI. And I think with that, we will see a big upswing, especially on medium voltage GaN, whereas so far there was a lot of focus on 650 volt high voltage gallium nitride.
Okay. Thank you. Thank you very much. Do you happen to have any final comments that you wanted to make before I close out?
Yeah, thanks a lot for your interest. Obviously, I'm from the GaN business at Infineon and I believe in GaN. Yeah. But I also want to say is that I think at this point in time, a key strength that Infineon has and overall in the industry that we will see is the coexistence of silicon, silicon carbide, and gallium nitride. Every technology plays in its field, I would say, today. And yes, this shifts over time where they are stronger and where they are maybe retreating. But all three technologies are typically having them and putting them into a system in the right spot is, I think, the key to success when it comes to best performance at a certain cost point that you want to achieve. And I think this we can offer, and we work a lot here also on system solutions that we can support customers in this direction.
That's very interesting. How do you see that coexistence, playing out, say, in the next, say, 5 years, silicon GaN and silicon carbide, what applications, might, how do you see it playing out?
So high level speaking, I would say that this very high performance, power density driven and high efficient applications like AI, IBCs, they will transition more towards gallium nitride, I think. There are other applications that maybe have slower switching frequencies where power density today might not be the biggest topic, like motor control in certain areas. There probably it's more of a silicon play. Yeah? And then depending on how the environment is, where the application is operating, it might be again more of a silicon carbide play. Yeah? So I think it's always really depending on application, what is the cost point, what is the performance point that you want to drive.
Gotcha. Thank you so much. I really appreciate your time. It was a really insightful and illuminating discussion.
Thank you very much. Thanks for your interest.
Thank you. Thank you, Anne.